Hi everyone, in this video I'm going to briefly go over the carbocation stabilities and talk a little bit about carbocation shifts. And so before we kind of get started, I just want to talk about why this is important. And so right now this may not seem super duper important, but when we start looking at reactions, we want to know which of those go through a carbocation intermediate. And so that's where it's really important to know the mechanisms, because if a reaction goes through a carbocation, we need to look at the stability of said carbocation and if it will shift, because that will change the final products. Just as like an overview, this should be kind of provided to you in a table. I didn't copy the entire table, but this is kind of the almost all of the carbocations that you guys may see and their relative stabilities. And so the least stable would just be kind of a carbon attached to 3 hydrogens. And so when we move to the right one, we can actually say that this is primary carbocation, and so is that one. And so what's really the difference? And I have kind of seen a lot of questions on Piazza regarding this, but the answer is hyperconjugation. And so we have 2 H's here, whereas with the first example, we have 3 H's. And so the other group is a methyl group, a CH3 group. And it's really important that you guys know that CH3 groups are sigma donors. So what that basically means is that through their sigma bond, they will end up giving a little bit of electron density. And that's good because carbocations are positively charged, and so they're already electron deficient. So the fact that the methyl groups are sigma donors, they're kind of helping to contribute to a solution, I guess, for the carbocation. And so kind of the next set would be a primary allylic. And so still we're primary, but we have that resonance donation. And so similar to with acidity and basicity, we don't want to have the charge only on one molecule. We want to kind of spread out the charge so that not only one atom has that positive charge, has to bear the positive charge. So in this case, we would get something like this when we do the resonance donation. And so obviously, if you have something like this, that would be more stable. Even though it's primary allylic, when we resonate, the resonance structure is a secondary allylic. So in that case, this would be more stable than that, because when we do the resonance donation, we have a more stable carbocation afterwards. So next up, we have secondary allylic. And again, you can kind of draw the resonance structure if you like. And then the next one is kind of weird because we're back to primary. So we had a secondary, but now we're back to primary. But in this case, it's primary benzylic. And so in this case, it's almost like a benzylic is an allylic on steroids, because we have the resonance donation like that, but we have it around all of the atoms or all of the carbons of the benzene. And so it won't be all of them per se, it'll be this one, and this one will end with the positive charges, but we're still donating the positive charge, I guess, to multiple atoms throughout the ring. And so again, if we can kind of spread out that charge across more atoms, it'll be more stable. So even though it's primary, we need to look at the fact that it's benzylic to come to the conclusion that it's more stable than secondary allylic. But in this case, the tertiary is more stable than this primary benzylic. And the tertiary allylic is obviously more stable because we have resonance in addition to the tertiary nature of the initial carbocation. And then finally, we have tertiary benzylic. So for me personally, I kind of was a little confused with this at the beginning, and I kind of found that this was one of those things that you had to memorize certain things, like how primary benzylic is more stable than secondary allylic, but tertiary allylic is more stable than primary benzylic. So just kind of stuff like that, it's good to know, but with practice, it will kind of stick a lot better. So that's just kind of the brief overview. But so this is kind of based on a question from the workbook, I think, and I've seen a few people ask. So I believe the question was to rank the following carbocation stabilities. And so kind of going back to unit 1 and acidity and basicity, the kind of holy grail of stability is full octets. If we can achieve full octets, it's almost always going to be more stable than something that doesn't have full octets. So when we look to the first two structures in this case with the heteroatoms, they have a lone pair and they're adjacent to a carbocation. So they can give the carbocation their lone pair or resonate their lone pair and form a structure that has full octets. It still has a positive charge because we haven't really kind of added or subtracted any charges. So the net charge should be the same, but we have full octets. And so the same thing in the second case. We can resonate that in and create a structure that has full octets. Again, positive charge. So that is going to be infinitely more stable than these second molecules, even though they have resonance, they are allylic, they will never have a full octet. And so right off the bat, we know that the first two have to be more stable than the second two. But out of the second two, we have a secondary allylic and a primary allylic. And so the secondary allylic will obviously be more favored. So we'll just go ahead and say 4 is the most stable. So this will be the least stable, second least stable, and then we look to our heteroatoms. And here, again, we kind of need to pull from acidity and basicity and our knowledge of electronegativity to come to the conclusion of which is more stable. And so oxygen is more electronegative. It is holding those lone pairs closer than the nitrogen because it's more electronegative. It wants to hold on to them more. Nitrogen is more basic. It's more kind of willing to give off their lone pairs. And so we have that resonance with nitrogen more so than with oxygen because nitrogen, again, is more kind of just willing to let the lone pairs go. So nitrogen will be the most stable because it's the most giving of electrons, and then oxygen, and then 2 and 1. And so this is kind of like a side note that I would be really surprised if they brought up on the exam. But if they had something like this, with sulfur and oxygen, here we need to look at atomic size because remember, as we go down the periodic table, we want to look at size, and as we move across, we want to look at electronegativity. And so what actually ends up happening is from a molecular orbital standpoint, because sulfur is so much bigger than oxygen, we have kind of worse resonance. And so it can resonate a little bit, but because sulfur is so much bigger, the orbitals have a harder time overlapping to form the pi bond. So in this case, this would be more stable. Again, I don't really think that they would really test you on that, but it will be important to kind of be able to justify that if it does come up. So just kind of going through carbocation stability, that is really kind of like the only one that I saw that had a lot of questions about it because it is pulling from past material. So now, one of the trickiest things with carbocations and when we have them in a mechanism is that they can undergo carbocation shifts. And so kind of what we were talking about before with the stability, if something's not stable, it's going to want to move into its more stable form. So if we have a primary, it's going to want to go to its secondary if possible. So that's kind of what the idea behind these shifts are is, they're not in a good place. Let's make a chemical change, and then we will have the carbocation in a more preferable place. So in this first case, we have a primary, and what we can do is we can use a methyl from an adjacent carbon, move the methyl to where the initial carbocation is, but because we are taking that electron density from this pink atom, now that pink atom is going to have a positive charge because now it's lacking electron density. So we took electron density from the sigma bond between the carbon and the H, and we just moved it to its neighbor. And so now the pink doesn't have that, so it is going to be positive. But if we look at the stabilities, we go from a primary to a secondary. So that is a win. That is better. When we look at the stability, secondary is more stable than a primary. Now, when we have a benzene and a allylic radical, or I'm sorry, not a radical, an allylic carbocation, you may want to say, well, we'll do a ring expansion. But in this case, it kind of goes back to what has been hinted at, probably not talked a lot about, but the fact that this benzene is what we call aromatic. And I'm not going to really kind of go too much into detail, but what that really means is that the benzene is very stable. You know, we're not going to touch with it, or we're not going to touch it, we're not going to mess with it. It's very stable. If we did a ring expansion, we would break the aromaticity, and that would be bad. We don't want to do that. So in this case, there will be no shift that happens. And so that is kind of important to know, that we just leave benzene alone, especially in this class. In Orgo 2, you may talk about reactions with benzene, but it won't really expand like, in this case. So the next thing, and this is kind of a big one that I've seen on Piazza and GroupMe, is that we have a secondary, and if we go to a secondary, we can then go to a tertiary, and that is favorable. But the thing is we're going from a secondary to a secondary. And so, these molecules can't really like look ahead into the future and say, they can't turn their or peek their head outside of the corner and say, if I jump forward to become a secondary and then turn my head, then I can see that there's going to be a tertiary, so I'm going to do it. They can't really do that. This is a horizontal move. We're going from a one stability to something that's equally as stable. And so it's never really going to happen. So although we could end up in a more stable position, we wouldn't go through an equally stable intermediate in this case. So again, this one would have no shift. So in the next example, we are starting off with a secondary, and instead of moving a hydrogen, in this case, we don't have any hydrogens. And so we have to move a methyl. And so we'll move a CH3 group, and we will get this. So again, keeping in mind which atom is going to end with the positive charge. In this case, it really doesn't matter since it's symmetrical, but we are taking the electron density from the pink and moving it to the green right here. So the green initially needed electrons, and the pink said, I'll be nice and I'll give you this methyl group. So now the pink doesn't have the methyl group, it is now lacking electrons, and so that will be the carbon that bears the positive charge. So I don't know if I have an example on this. Yeah, I don't think so. So if we have something like this, where we have a hydrogen and a methyl, well, what are we going to do? Are we going to move a hydrogen or a methyl? And the answer is we're going to move a hydrogen. And so that's because the affinity of hydrogen to move is greater. And so it's kind of like, a moving truck. You don't want to take a big bulky group with you if you don't need to. If you only have to move a hydrogen, it's a lot better than having to send an entire methyl group to your neighbor. So the next kind of portion, I guess, is ring expansions. And so I know that this is really kind of something that takes a lot of practice, but it really is important that you guys like stay organized here, because it's really easy to lose track of something, and you really don't want that to be like the reason that you miss points. And so with ring expansions and ring contractions, I always label the carbons that are either initially part of the ring, if we're doing a contraction, I label the ones that are initially part of the ring, and if we're doing an expansion, I label all of the ones that will kind of be in the final ring. And so that may not have made a whole lot of sense, but in this case, we'll see that this bond is almost going to like swivel out and kind of open the door almost to form that bond, because if we remember the cycloalkane stabilities, the cyclohexane is kind of like top dog. It's almost like a curve like this. a parabolic curve, whereas 6 is kind of the peak stability. If we move to the right and we go to 7, it's not as stable. If we move to the left and go to 5, it's not as stable. And so if we're at 4, we're here at 4, a move to 5 is going to be more stable. And so we're going to do that. And so although, our end product may have a secondary, whereas in this case we have a tertiary, the amount of energy that we kind of gain from expanding the ring by releasing the ring strain is much, much more than going the kind of the downsides of going from a tertiary to a secondary. So that's why in this case, we will do a ring expansion. And so we'll go from a 4-member ring to a 5-member ring by, again, swiveling it out like that. And so I will count 1, 2, 3, 4, 5. And then I will draw the final ring kind of backbone, 1, 2, 3, 4, 5. So 1 has these 2 methyls right here, and nothing has removed those methyls, and so 1 will continue to have those methyls. But with the kind of conservation of charge, we have a positive on the left, so we have to have a positive on the right. Nothing, donated electrons to that molecule. It was just an intramolecular interaction. So we have to have a positive charge. And so with practice, this will kind of come a lot easier, but I'm just going to almost narrate it so that it may help you kind of connect those ties in your head. So this bond right here between carbons 2 and 5 is being broken, and this bond between 5 and 1 is being formed. And so again, kind of similar to the fact that we're taking electron density from one atom and giving it to another, the same thing's happening here. We are taking electron density from 2 through this bond and giving it to 1. And so we're stealing from 2, giving to 1. Therefore, 2 must have the positive charge, something like that. And so in this case, you may have changed the numbering order, or, if it was clockwise versus counterclockwise, you could have ended up with that carbocation. It really just kind of depends on which numbering order you had. And it is kind of going back to with stereochemistry, important that you guys can recognize when molecules are identical. So we will do a ring expansion and end with that product. And so with the next example, we have a cyclohexane. And so going back to this graph, cyclohexanes are the top dog. So if we are not going to want to go from a cyclohexane to a cycloheptane, because that's going to have more ring stress. And so in this case, there will be a shift, but it won't be ring expansion. It will be a hydride shift. And so we have a hydrogen here, and we're going to move it to there. And we are taking electron density from that tertiary carbon, and so it's going to be that. And so in this case, this is another example of a potential ring expansion. And so we have a cyclopentane, and if we expand, we'll have a cyclohexane. And so that is favorable, so we will do it. And so now in this case, I will number 1, 2, 3, 4, 5, 6, so that all of the carbons of the final ring are going to be accounted for. So I know that it's going to be a 6-member ring. So it's going to have that kind of backbone. And then I'm just going to go ahead and number. Again, doesn't really matter where you start. And so 1 has this ethyl group like that. And so we're going to put the ethyl group on 1 like that. And so 3 also has a methyl. And now we need to figure out where is the carbocation. And so the bond between 2 and 6 is broken. The bond between 6 and 1 is formed. We're stealing electrons from 2, giving it to 1. Therefore, the carbocation will be placed on 2. So those are some examples of ring expansion. And so this example right here is going to be a ring contraction. And so these are a little bit trickier because they're a little bit harder to see, because instead of expanding, we are kind of forcing it to be a smaller molecule or smaller ring. But in this case, again, going back to this graph, we have a 7-member ring, and it will be more stable if we go to a 6-member ring. So that is what will happen. This, I'll go ahead and number 1, 2, 3, 4, 5, 6, 7. And so we know that it's going to end in a cyclohexane. And so in this case, the bond between, you could either look at it between 3 and 1 is going to form, or 6 and 1 is going to form. Really doesn't matter. Kind of whatever you want to do. Actually, I'm sorry. It will be between. I think it will be, yeah, between 6 and 1. So when we go ahead and then number, actually, we know that there's going to have to be one more methyl because we start with 7 carbons and then we have to also end with 7 carbons, and so there'll be a methyl group. So when we go ahead and number, you can number like this one. That will be 6. Wait, I'm sorry. This will be 7, 6, 5, 4, 3, 2, and then that will be carbon 1. And so this, obviously, as you could probably see, I'm struggling with it because it's a little bit, again, more difficult to visualize the contraction versus the expansion. But again, it could happen. A lot less likely, I will say. I've only ever seen a few examples of contraction. But again, we need to figure out where is that positive charge going to be. And so we are breaking this bond between 6 and 7 and giving it to 1. And so the carbocation will be placed on carbon 7. So yeah, especially with contractions, it can get a little bit confusing, but definitely be ready for this because I've seen on practice exams, they'll have you rank stability of carbocations, figure out which ones will go through shifts. So those are 2 questions where it's only carbocations. And then in other questions that may require you to do, or the mechanisms may require a carbocation, you have to recognize that, okay, I need to look for shifts. I need to look for expansions. I need to look for contractions. That will be very kind of important. So this stuff may not look like there's a lot of points associated to it on an exam, but since a lot of mechanisms that you guys learn do go through carbocations, it's really important that you have an understanding of the stabilities and shifts and stuff like that. So this one was probably a little bit long, but hopefully it answered a few questions because I have seen a lot of questions about this in the Piazza and GroupMe. But if you have any other questions, feel free to reach out on, again, GroupMe or Piazza, and someone will be able to answer. Have a good one.